Dirk, a question? Oh, no. How many think I should go ahead and just say something on my own spiel?
Wait,
No
I want the
hands.
option for
no
both.
hands.
I want the option for both.
Go ahead.
I want the option for both.
Oh, gosh, everything.
You have two hands?
Yeah.
For both, too.
Well, Dirk, you mentioned two very different sectors, light matter and the machine learning, optical computing. By the way, how many of you ever heard of optical computing before? Yeah? Do you know, so I worked as an undergraduate here 30 years ago. I went to Bell Labs and worked in the optical computing department at Holmdel. And I saw my boss go off on ABC Nightly News on television, if you've ever heard of what that is, and say to the world, at that time the world did watch TV, that their electrical computers were going to be replaced by optical computers with photons going through the circuits and no more electrons because it was faster, it was lower power, it was much more capable of instantaneous matrix multiplication.
Oh.
What happened? I went to meetings just like this with all of you optical computing enthusiasts sitting in the audience. What happened? The field crashed and burned. And then turned into a telecommunication revolution, which has changed the world, but in a completely different way than expected. So, Dirk, how would you compare and contrast your quantum controllers effort with the two amazing startups you've already spun off, like Light Matter on machine learning? Which one is going to have higher impact? Which one do you believe more in? Which one are you more excited about for the students today?
I don't pick any favorites amongst children. So I think I don't have anything against electrons. I don't have anything against photons or for photons. I think they're all great because it is true that people in the 1980s already recognized the potential of optics in computing. It takes Fourier transforms automatically. It does do matrix multiplication ultra fast at the speed of light, and you can do many fascinating things with it. And then came the electrons and CMOS scaling and so on worked terribly well. But I strongly believe in reasoning things through from first principles. So don't let the past failure of this or that dissuade you. Like, why didn't it work? It didn't have a fundamental reason it didn't work, if you look through it. So a lot of people say, oh, optical computing, it can't work. And I think I said it sort of, to inspire some conversation here, right?
Yes.
And people say, oh, it's been tried. Well, electric cars had been tried in 1880. I think one of the first the first automobile, some of the first automobiles were electric. I think maybe the first. Yeah. And Mercedes-Benz came along, developed a combustion engine, and perhaps unfortunately they took off. But now we see a resurgence of electric cars. It was never a bad idea to make electric cars. The technology had to be right, and things are lots, like there's randomness, right, in technology and in society. And so, but we can hope that generally we go in the right direction. Hope. So optical computing has a lot of inherent things going for it. Like you can compute at a ridiculously low energy consumption. And which one is going to be more impactful? I don't know. I have really no idea. And I don't think about it that way. I'm not placing bets. I do it because it's fun. And as long as it's exciting and we can learn something, I'm very happy to invest my time in it. I guess one thing I would say about the quantum computing, the way I would describe it there is I invest my time into it because on the one hand, like it's a lottery ticket that there's some probability that in this cycle it will actually sort of revolutionize technology, maybe by the end of the decade or so. And that's a guessing game. Right? I don't know, 10% chance, I would say. Maybe by the end of the decade, we will have maybe useful quantum computers. I'm fairly optimistic on this, but I would say it's good chance, like definitely non-zero, and I think that's pretty awesome. But what I know for sure is that it's an admission ticket to new discovery, to understanding the world better, and that certainly is good enough for me.
What a beautiful answer. Isn't that great? What you have heard is do it for curiosity. Do it for possibilities that might help the world, a new quantum revolution. Do it for science. Do it because it can let you measure and control things you've never done before. Did you hear from anyone do it because it helps today's world, or you can actually build a bigger quantum computer to outspeed classical computers? No. And so what I'm doing in my work is trying to figure out an answer to that question. You know, one of the frightening realities of quantum computers today is that quantum algorithms, there are very, very few of them, very few new, truly new quantum algorithms. It's really just down to phase estimation, which is a generalization of Shor's algorithm. I hope you all realize this concretely. All these other variants that do different forms of like nitrogenase quantum simulation, or you name it all. They're just variants of one algorithm, including Harrow-Hassidim-Lloyd for linear systems. That's a variation of Shor's algorithm as well. So one of the interesting stories that my group was able to discover last year is that Shor's algorithm, the simulation algorithm of Seth Lloyd and Richard Feynman, the search algorithm of Grover, which has a square root speed up, they're actually all the same single algorithm, literally, exactly, mathematically. And we have a paper called The Grand Unification of Quantum Algorithms. And each of these algorithms is described by a single vector of real numbers, phases, and the structure of the algorithm is exactly identical, and it is quantum signal processing, the kind of stuff that Will was studying. And that means that we encompass all of them in one framework, but we don't yet know what really new quantum algorithms exist, even beyond this. And I think this is a really big problem for the field, because really, it's missing VisiCalc. I don't know, you don't know what VisiCalc is, sorry. Is the single application that made personal computers take off and actually become economically important and useful, done by the folks who ended up like Mitch Kapoor and stuff, and who set up Lotus over here. That's our big problem for the field today. The reality is that quantum computers are not economically useful today, exactly like you said. There is that word, the today. It might be tomorrow, but I think it's going to depend on you here. Those of you who have creativity, who have come from different fields, have different problems, that can come and see what quantum computers might be able to solve that we haven't thought of before. That's why I think you're important. Because at the same time right now, I also talk with a bunch of colleagues who are busy building a Noah's Ark for the field so that they can bring in two of the best of everyone for the period that might be coming. Well, the word is quantum winter, so that the field can be rescued through its trough of disillusionment and will still exist in 20 years from now and can revive itself. There is this sentiment going around, and you've got to know about it, because it could go that way or could go a different way, but it's depending on you here. So welcome to MIT.
I have a follow-up question for you. So, Peter Shor came up with his factoring algorithm in his head, maybe on pieces of paper or using a small conventional computer. But the person who came up with VisiCalc, I don't think they pictured the whole program in their head and just like wrote it out. Do you think it's going to take actual people working on actual quantum computers, like these students, to come up with these next applications? Or do you think because of the kind of inherent structure in these quantum algorithms we've seen so far, that it's really going to take this, I guess, the strategy that's resulted in the existing algorithms so far?
What a great, wonderful question. Peter Shor, the story is the following. Peter Shor was homesick, and he was reviewing a paper. You know, academics review papers from peers to try to see about acceptance in a major conference. That's what Peter was doing. And by reading this paper, he got an idea, and he happened to know that if you could find periods in a certain function, then it could solve the factoring problem of integers. And the paper did not connect it with the problem, but Peter knew the problem, and he connected them together. He had to add a piece, which is to make appropriate Fourier transform. So, as you hear from Kevin, what is needed is not just somebody sitting in a room, but somebody who has the two pieces together, the problem, the knowledge of what is possible. I think you would say the same in Sloan for all sorts of emerging technologies, in chemistry, in solid-state physics. You've got to know those two basic pieces put together. So I cannot, as myself, just sit in a room and invent something like this. I think it really takes a vast diversity of experiences and understandings of what is needed and what problems exist in other fields so that you can overcome this and come up with the right innovation. It's actually a fun thing to ask oneself, what is needed for innovation in a field? And it is a lot of these kinds of ingredients. And by the way, I'm thankful for all of you taking my questions so well. I hope you realize I treat almost every interaction like an oral exam. And it is your turn to get back at revenge at me as Kevin is demonstrating.
I don't know that it's revenge, but I do think that your singular value decomposition paper that you just referenced from last year, the unification of quantum algorithms, I think that's why that's such an important paper. And I haven't had a chance to tell like this, but I think that's such an important paper because what you just said, I think, is so true that you need both pieces, right? And so by being able to abstract all known quantum algorithms into a single framework allows more people to understand the quantum algorithms that we have today. And then others who have different life experience, different backgrounds, different expertise, can now understand quantum algorithms in general, and then ask, okay, with this framework, how do I now apply that or tweak those phases, so to speak, to apply to this problem, right? And it's so important because before this paper, there were these different classes of algorithms, but how they connected to one another, it was almost like we just grabbed different ideas out of space somehow, and they gave either quadratic speed up or almost exponential, but they're the same. And that's amazing.
Thank you. What's the question?
Oh, there was no question.
Okay, actually, there is an implied question there, which I'll ask myself. What in the world is the use of all of this if I've just shown a general framework? What do you think?
Oh. Well, do you see how he did that? He turned the question around to me. He's very clever, this guy. So the reason it's, if you think about engineering and science generally, what do we do? What do we do over and over and over again? We abstract, and we try to reduce and understand things at a fundamental level. We see two things that might be related, but they're disparate to us in our understanding. And then we dig into it and we realize, oh, if I just understand this higher level concept, then I can understand both of these by this framework, right? And that's what I think the importance of this algorithm is it creates a framework for people to think and understand quantum algorithms and then take the next step.
We might speculate further along this line because it's not necessarily a mathematical problem alone that might be solved. It might be a game theory problem. It might be something that involves multiple parties in a market together. Like, what is a quantum auction? And people have looked at in previous hackathons, what is a quantum chess game? When you have multiple parties with differential knowledge and different goals and ambitions and capabilities. And quantum changes the rules of many of these things, changes Nash equilibria. But we don't know the right way to think about this today. So maybe it won't be quantum computers, but it might be quantum networks with sending qubits back and forth somehow. Or it might be quantum sensors, when queried in the right way, with some molecules being purely classical, some others being partly quantum, and some being purely quantum. It might be an interaction of this funky grand unification model acting as a neural network, co-processing together with Dirk's light matter processor. These are real possibilities, and I have no idea what the answer will be there because I don't know the right problems. And that's just one of the fun things about interacting with the marketplace, because it might be that Mercedes-Benz coming along with some interesting market problem, yeah?
And I'll add one other complexity, as if it wasn't complex enough. The market's not static either. Over the time frame we're talking about, loads of other variables, loads of other technologies are going to emerge, become redundant. So it's a fun and interesting and complex future.
Right, and they're competitors. I mean, why are we working on quantum computers instead of working on the ability to build our computers into DNA strands so that I can just put it in the ground and water it and have a computer grow out of the ground. And then solve all of our food problems without nitrogenase being fixed. You know, there are amazing things we could be spending our time on, but you've got to be creative about it. I hope this is reasonable.
I have a question for you.
Oh, go.
I do have a question for Ike. So, and it's related to what you're going to be doing over the next 24 hours. I would love to hear your thoughts on this, because I think about it sometimes. You're going to program a quantum computer, right? And if we look at let's take a step back. If you look at conventional computers today, you represent the program and you represent the data and you process that data, and it's all the same transistors. And that's called homoiconicity. Everything is represented the same way, the instructions as well as the data. But what you're going to do tomorrow is different. It's heteroiconic. You're going to program a quantum computer, and the data are quantum, but your program is done on a classical computer. And that's how we do all of our programming today. And I'm asking Ike because he just unified what we know about quantum algorithms within this heteroiconic framework. And I'm wondering, what do you think about a homoiconic version of programming quantum computers?
That's a fantastic question.
Thank you.
I have
Please tell me the answer.
I have no idea. Next. No, honestly, Will. Look, today we're actually moving in a very interesting direction in computing, high-performance computing. For the first time, we not only have CPUs, but we have GPUs. We have co-processors at all sorts of levels, different levels of caches, for example, and we need to harness all of these. Remember, think of Google. Google is one of the biggest computers in the world, but it's a distributed computer, unlike just a computer you have on your desktop. A whole slew of new ideas had to be developed to harness distributed, fault-tolerant classical computers. We haven't even begun to think about distributed, fault-tolerant quantum computers, much less the fundamental questions that you're asking just now. We need new programming languages.
That's right. Yeah.
Yeah. And if we're going to have auctions, we're going to have communication networks as part of this and protocols for communicating quantum bits sometimes and classical bits at sometimes. You know what this whole networked system looks like? Biology or chemistry. It really is what is happening at the low level of real chemical systems. Actually, tell us about photosynthesis. Isn't it a lot like this? Not to ask you a question
I
or
probably
anything.
don't have enough time to describe the entirety of photosynthesis.
You have 9 minutes.
But yeah, I mean, your photon management and your electron management comprise a very large part of chemistry overall, right? If you think about any light-activated reaction, thinking about those transitions between different energy levels, there are theories about potential quantum interactions that have to do with the light, but we're going to stay away from that field for now. And then chemistry fundamentally has to do with the movement of electrons. I mean, that is the entire field. How many of you have taken organic chemistry? Oh, that's awesome. That's so much more than I thought. Right? You spend all of your time in organic chemistry using arrows to denote the movement of electrons. I mean, that's what you do. You have an arrow, and your arrow shows your electrons going from point A to point B. And that is a whole year of organic chemistry. I mean, there are other things, but that's it, right? That's a mechanism. Your electrons move in this way, and they always move in this way. And you can think about processes like tunneling. An MIT chemist in my department, Joanne Stubby, has done amazing work on one of the mysteries of biology, that in an enzyme called ribonucleotide reductase, you have an electron that somehow manages to traverse 35 angstroms without stopping. How does it do that? Does it tunnel? Does it tunnel for part of the way? Is there some sort of invisible chain? Anyway, this borders on quantum communication, thinking about how we transmit these objects that are inherently quantum, electrons and photons, across interfaces that we can't fully characterize, that we can well characterize.
Yes, yes, and the thing that you were avoiding talking about there is this paper from Berkeley that is showing that photosynthesis might be Grover's algorithm in action. Yes?
I'm familiar with that work.
Yeah, and isn't that a fascinating idea that your plants are generating energy, harvesting photons and turning that into ATP and ADP from ADP to ATP because of Grover's algorithm? It actually might be correct. I mean, it seems like nature is using a lot of these quantum coherent evolutions as heterogeneous blocks of not maybe computation, but
No, I mean, there are multiple types of coherences, right? There's electronic and vibrational coherences, and in different forms, those could contribute to a lot of plant biology. And there's an entire field of so-called quantum biology, which is largely devoted to studying the potential quantum components in these biological systems, a large part of which was kicked off by Graham Fleming's paper, which was just referenced.
yeah. So in some sense, Dirk, in your future, maybe it won't be light matter, but like chemical light matter or something, because you might harness many of these heterogeneous units.
Yeah, it's still light matter in that case. But my students started the company, right?
Yes,
It's
yes,
their
yes.
choice of name. But I would, by the way, the photosynthesis, I thought you wanted some decoherence there.
Isn't that tricky? Everything you're going to do in the next few days will abhor decoherence. But the reason you're alive is because of decoherence. Yes, absolutely. So
The random walk of, it's this random walk of this excited state of, in this molecule. And some argument is that it's an interplay between coherence and decoherence
And
that makes it sufficiently efficient.
Dirk
I don't
has to
want
be
to.
correct.
I don't want to cut off this fascinating conversation, but we only have 5 minutes left. So I wanted to ask our wonderful panel if they have any words of wisdom or advice for the young folks about to embark on this hackathon. Please start in whatever order you prefer.
Okay.
Dan,
Dirk is
Dan, if
about
you'd
to
like
talk.
to, or Dirk, if you'd like to start. Not to pick on you.
Question everything. I think that's one thing we've learned from here. Don't just don't take somebody's word for it. Just question it, think it through, and don't shy away from trying something really hard. If you succeed partially, it will it's a net benefit, I would say. So as you program, try the tough thing, and if you go even halfway or some partial way towards that goal, you've done something great.
I would encourage you to use this hackathon not just to build your technical skills, but to build mini communities. So become friends with somebody, talk to loads of people, find your tribe that you can talk about these challenges and these technologies beyond the hackathon.
Look to the fundamentals. Don't just try to optimize for the short term, but look to where you want to be in 10 years and move systematically towards that end.
Yeah, and follow your passion. Think, but don't think for too long. Act, because when you do things, things get done. It's amazing. And so, have a great time over the next 24 hours doing things.
I don't know how I can follow all of that. There are a lot of entry points to quantum, broadly speaking. I think my best advice is in the MIT Museum, the room with all the mechanical exhibits is really soothing if you need a break. I love the chair that comes apart, very relaxing. Good luck.
Good luck.
Good luck, yeah.
We conclude our wonderful panel. Let's thank our panelists again. I wish we had another hour for that.
Nascent market. It pales in comparison to the complexity and ambiguity that's inherent in quantum computing. So that sounds like a real challenge, and that's what drew me into being interested in it. And then the final bit I'd add is that I feel very lucky to be in the Sloan School of Management. There's very few places, I think you could probably count them in one hand, where you have a business school that is in the same institution as having world-class researchers in quantum computing. And so, to some degree, I feel it's a challenge for us that here at MIT and at Sloan, we need to step up to and be the community that's leading the thinking on the business of quantum computing. So that's kind of what brought me here today.
Hey, everybody. My name is Dirk England. I'm a faculty here in electrical engineering and computer science. I started majoring at Caltech in physics and math, and I was interested in understanding the universe better. I was initially going towards cosmology, but then towards my junior year, I was sort of missing the constructiveness of experimental research, or being able to do an experiment, not just observe, but actually do an experiment, and by that way try to understand nature better. And then I joined the laboratory of Hideo Mabuchi, who had just started at that time in atomic physics, working at that time with Jeff Kimball. They had sort of a joint group. And so as a junior, I started to work in the lab, and it was fascinating that, like, you could, on the tabletop, you could explore the frontiers of physics right in front of you. You didn't have to look up in the stars. And much of what sort of expresses that was a different way of fundamental physics that touches on information theory. Really, information theory might be the best way to describe the basic principles of physics. And in this way, really, I started to go into atomic physics, and then was thinking about Cambridge for grad school versus Stanford. I ended up going with the weather, so I went to Stanford. And I had this third connection here to Yoshi Yamamoto. I was joining at the time when Yoshi was just setting up a new experiment, and I would say I was going to, so at Stanford you can rotate, and so I was going to do Jelena Vukovic first, who was just starting her new group at that point, and then Yoshi after that. And I never left Jelena's group. And so I stayed in semiconductor quantum optics, and it's been going from here. But it's also a fantastic community, I would say, in quantum information science and in atomic molecular optical physics in particular. And so I think it's been a fantastic ride for me last 20 or so years in this field, and it's amazing. And it's a big surprise to see so many people now, so many young, awesome people who are going into this field now. I want to echo what Ike said also. Like, I think a lot of us initially were drawn into that field in part because it was unexplored, and so in quantum computing, and in this field in general, there are still so many fields that are unexplored. I don't follow the Troughton path. Like, there are many other directions to explore that in one way or another are connected to quantum computing. Quantum computing is much more than making a faster algorithm. It really teaches us about the fundamentals of nature. And so there's a lot to do.
Thank you all for telling us some of the things that inspired you to get here. So I'd like to go from the past to the present. And if you're willing, I'd like you to tell me one interesting question that you're trying to answer in your lab or group right now. Donna, if you'd like to start again, you're welcome to.
Sure. So what my lab does is we use chemistry for quantum information science. So we use the ability to put atoms exactly where you want to control both physical and electronic structure. And that's kind of great for quantum properties because precise control is everything that we talk about. Most of our work is focused on quantum sensing. And right now, actually, where I was half an hour ago was working on a manuscript draft that I'm really excited about, predicting whether a molecule where you can read out spin information can sense a local magnetic field of, for example, a 2D magnetic material like chromium triiodide. So the space between the surface of the material, and let's say 10 nanometers away is essentially a completely blank space. Nobody knows what happens there. And so if you can get this tiny molecule right down there, you can start to answer questions about what happens to a local magnetic field in a 2D material. So both understanding those properties and designing molecules that interface with questions like that is something that we're really excited about. And we're also excited about a lot of biological applications that I would be happy to talk about. But thinking about the magnetic field at chromium triiodide and whether quantum sensing in a molecule can help with that is probably where my head is at this particular moment in time.
Could you elaborate on one aspect of that? I'm really fascinated by the use of sensors in this odd way. How does the field of quantum information science and quantum computing help in the kind of vision that you just described?
So that's a good question. I'm not sure I would call it quantum information, right? Quantum technology, broadly speaking. But so the way that you would read out a magnetic field locally, and we could have an extensive discussion about what quantum means that I think you would have a lot of insight into. By modulating so you're creating a local magnetic field and you're changing your splitting of your M sub S levels, and you're changing not just your axial splitting, but your rhombic splitting as well. And so that should give you, especially because you can specifically orient molecules relative to a surface, that should give you spatial resolution for the magnetic field. And so optically reading out this information, just like NV centers, you should be able to get an optical probe. Now, is changing the separation of M sub S levels truly quantum? That's broad discussion.
I think I would agree with you, but if I may translate you.
Oh, yes,
Let
sorry.
me see if I got the translation correct. Does this mean that an iQuackathon student who's working with Qiskit might be able to come up with a sequence of control pulses for your molecular system?
Yes.
Which would then contort it in such a way that it'd be able to sense better?
Yes, quite possibly. That is a really great suggestion. And because I'm a chemist, a lot of the actual quantum operations we do aren't necessarily more sophisticated than what a, protein structural biologist would do with nuclear magnetic resonance to decipher structure. You do a lot of correlative spectroscopy. And we were just talking before the panel started about one of the pioneers of this field, Alex Pines. And so the library of ways to control pulses and magnetic resonance is broad. And my lab effectively steals that existing technology because our main contribution is making and designing the things, and then we borrow the technology. But there's this amazing space in between that Ike is really pointing to with the ability to control this at a more sophisticated level.
So your message to our audience here and out in the virtual world might be that everything you're doing that you think is working on quantum computation could actually make chemistry better.
Yes.
Oh, there's a but coming.
There's a giant caveat. One of my personal crusades that I think at least Will has been unfortunately subjected to is that the space of quantum computing as applied to chemistry requires more caveats than is frequently expressed.
What's one of those caveats, though? Because actually, the reason I'm keeping you from going on is so that I can say less later, but also because and this is important to y'all. I think what Donna is doing is actually useful. Okay. Seriously.
That's good. I'm not sure I do.
But more useful than a lot of what's happening in quantum computing today. So what are one of the caveats? Because really, there are real big problems.
Yeah, so I would say that the phrasing the questions correctly is really important. So one of the, so to pick on approximately half of the sponsors of this event, one of the classic things that you'll see for why quantum computing is useful is to understand things like the mechanism of nitrogenase. I mean, have you seen these slightly horrifying Google videos with some guy standing in front of a cornfield? Anyway, they're There is an enzyme that turns N2 into ammonia. It uses the process that we use commercially, the Haber-Bosch process, uses 2% of the world's energy, et cetera. This is very close to my field. But the problem is the argument that you're going to use a quantum computer to find the ground state of a catalyst to understand it better does not hold water, because the ground state is intrinsically not the thing that does the thing, right? So, and I'm not saying that this is a bad area, actually. I think nitrogenase is a fascinating and important